Welcome, everybody. Today's topic, of course, is going to be analyzing with P-Delta. This is a presentation that we're really excited to give because it is a very hot topic here in the office. Usually around once a day we get a tech support email, if not more, on P-Delta. So if we can help explain this a little further and dive into it, it's a great tool for everybody to learn a little bit more. So specifically what we're going to be doing here is we're going to be talking about the what, why, when, and how. So what, really we're going to start addressing what P-Delta is. Some of you that might be review, but if you're not familiar with the different types of P-Delta, this might be a refresher for you or a brand new topic. We'll also be talking about why we're concerned with P-Delta. When do we have to apply P-Delta, and how do we actually get through some of the P-Delta problems that we're going to have. Inherently, P-Delta might cause your model problems, and that's probably why most folks are watching today, because they have experienced problems. So how do we get past that? So the definition of P-Delta, a lot of times you'll hear people call it a P-Delta effect. You know, I found a couple definitions, and they're long-winded, but this one I found here is a destabilizing moment equal to the force of gravity multiplied by the horizontal displacement a structure undergoes as a result of a lateral displacement. Really what that breaks down to, and the name P-Delta is really the definition. P is the force of gravity, and you multiply that by the delta, or the horizontal displacement. So it would be something, we also call this sort of leaning column, but what it's really addressing is how the force of gravity is really going to be causing displacement, and how that affects the stability of the structure. So this, you know, the what is we can kind of look a little closer at a column. If we look at this is sort of our classic RISA explanation, and let's examine it a little bit here. So if we're looking at a column, it has some force on it, or P, and that's shown in this picture. The length of that column is listed in L, and that's its undeflected shape. So as that model or that column deflects, there's a certain delta or horizontal deflection there, and that would be what we call the delta in this P-Delta example. And so what we'll see here that we get that we're going to take that delta and we're going to find some secondary shears that are caused in that column due to that deflection. So it's almost as if that column loaded with gravity is leaning over. So we use the equations here. The force itself times the delta, P times delta, equals the shear times the length of that column. And then what we try to do is solve for that secondary shears. So we reformat that equation to get the V, or the shear there. Internally, so what we do in RISA now is we take that model and we take the V that we've calculated for, and we apply it to the nodes. Now that's an important note, that the way P-Delta is handled inside of RISA is nodal. So that means that we're applying that shear, that secondary shear V, at each node that's located in the model. And then it gets rerun. This is all internally, so you'll see if you run a model that has P-Delta things going on, where you see it running P-Delta chugging along in the background, it's running that, it's applying that V, keep solving it, and it's going to be resolving it behind the scenes. So you're not actually doing this resolving, it's doing it for you. And then what it will do is it'll iterate until it finds a deflection in which it converges. So what we're looking for is stability, for the actual column to have enough resistance to stop deflecting. So as we keep applying shears, it now converges and doesn't deflect anymore. So this is the process that we would go through internally when you turn on P-Delta in RISA. What we've got here is also something that's called little P-Delta. So the one we just discussed is what might be called a big P-Delta. The other type of P-Delta is a little P-Delta, and that really accounts for the curvature of the element. So if we look at the model above, what we've got there is a big P-Delta, which is actually this little delta sign above my curvature word. That's the deflection from the top of the column, or the entire length of the member column, from that to the bottom of it. So you're looking at the entire deflection there. While you're looking at little P-Delta, you're seeing that that's actually curvature of the member along its length as it deflects. So in RISA, how we implement little P-Delta is that we add intermediate joints to the element. So in this example that we're looking at on the screen right now, we see that there's additional nodes along the links, and that what will happen if you add those nodes, since our P-Delta inside of RISA is nodal, that there will be secondary shears calculated and applied at each one of these nodes. So it will basically go through this and will mimic the effects of that curvature. So we're going to go through an example of how that will work, but we'll see that that's the little P-Delta. Now, why do we do P-Delta? That's a good question to start with. P-Delta is required by code. So it's been around that we've seen some of the codes require it along the way. First, 13th and 14th edition required it for the design of stability, and that specifically is the direct analysis method. So what you'll see is there's second order analysis for big P-Delta and little P-Delta required. Little P-Delta, sometimes you can get out of that. It depends how much axial force you have in your element, whether you can avoid doing little P-Delta. But I'll show you how to do it just in case you do need to qualify that for the second order analysis. So what we also have is that now the ACI 2008 and the 2012 require P-Delta as well. There's three types of things that they actually have listed here: nonlinear second-order analysis, elastic second-order analysis, or moment magnification. And what you can do is use the elastic second-order analysis to account for, which is using the P-Delta effects, to account for that in the concrete codes. So you've got that in place, and then you also have some foreign codes that have had it for a while here, CSA, some other ones as well that you may have had to account for this in the past as well. So we have some reasons, and it looks like more and more codes are trying to adopt the P-Delta effects, so we're going to want to make sure we pay attention to it. So the when are we supposed to be worrying about P-Delta? This is often a common thing. So we know we have to account for P-Delta, but in our models, a lot of times people are going to be doing their models in some stages. So you'll lay out your gravity system. You'll put all your gravity, your dead loads, your live loads, and that probably is not a time to address P-Delta. What P-Delta is going to do is destabilize the model. So if you're just doing your gravity system, you might not be ready for that horizontal shear force. It might not be stable enough. So as you lay out your gravity system, maybe you just worry about gravity, keep P-Delta turned off. Then as you design your lateral system, this is where you might say, okay, I'm laying out my lateral system, I'm applying any wind loads, any seismic loads, so I'm actually applying loads in the out-of-plane direction, so or even in plane, whatever it's going to be doing in the horizontal direction of my model. So now I actually maybe start to turn P-Delta on. But you would want to make sure that your model is actually withstanding the wind loads or the seismic loads that you've applied, and then maybe go ahead and turn P-Delta on. At the very end, in your final design, of course, that's definitely a time when you want to have P-Delta on, so that your final design accounts for P-Delta. But the fact is that you don't need to include it from the very beginning. You can start with just your gravity and make your life a little bit easier going through gravity system, and then build on that once you get to the lateral system and then their final design. So let's see here, P-Delta is definitely on the final design. So what I'd like to show you starting out with is an example. Let's jump into the program and talk a little bit about how P-Delta works in RISA. So let's go jump into RISA. So what I'm looking at here is in RISA 3D, and a couple things we want to talk about is before we even build this model, an example model, is how do you turn P-Delta on? So first thing you do is on this data entry toolbar, there's a load combination spreadsheet, and if we create a load combination, we can call a description, P-Delta example, and what we're going to do here is that we can, right here, this column which says P-Delta, if you click on that, you'll see that you have some options. If you leave it blank, it's not going to have P-Delta turned on. If you say yes, it will turn P-Delta on. And then if you say compression, we'll get into this in a little bit here, but that will allow only the compression members to be checked for P-Delta. And so let's just say no for now, but here's where you turn it on, okay? So we're going to build a model, but let's also talk about where that convergence. So when we build this model and we run through that P-Delta iteration, like I mentioned earlier, it will run through the model. It's going to converge on a number that's in your global parameters, right under the solution tab. Okay, we have a convergence. If I jump over to advanced tab, this is a little new, sort of a little bit down in the advanced there, you'll see that there's a P-Delta convergence tolerance. And right now it's at 0.5%. So what we're looking for is the model to not deflect any more than 0.5% difference, and that will then converge, and it will stop trying to apply secondary shears. So that's where you want to adjust that. This is typically not adjusted, but if you are having a problem and you really can't get past it, you might open up that tolerance. That might be something. Not usually, but that is where you do that. Now, when I mentioned you don't always apply P-Delta, let's talk about what that means. So you have a setting inside of your tools preferences. In here, we can see that there is a setting in the solutions and results that will tell you exactly. Right here, there's a checkbox, don't require P-Delta analysis for AISC, CSA, ACI, etc. Now, what that means is that the program will give me a warning that I did not do P-Delta, but it will give me results. This checkbox, when it's turned on, this allows me to do the gravity design and still get results. So what I do recommend is that you turn this checkbox on. Use that checkbox there. And that will allow you to step through the different phases of design and still get results. And that's sort of one of the, if you don't trust yourself to check P-Delta, I guess that might be something you uncheck, but typically you're going to get a big warning, and we'll see that. And so you'll be reminded every run that you have not run P-Delta. So let's see, what we're going to start with is just a simple column to sort of demonstrate what we have for P-Delta. So I'm going to start by drawing a column. And I'm going to go to I'm going to actually use a 12 by 45. I'm going to just type it in there, and I'm just going to call it a column, okay? And it's going to just draw it up here. I'm going to just draw a 12-foot column, and if I come up here, it's about 12 feet there. And I'm going to make sure it's a fixed bottom, so I'm going to go ahead and put a boundary condition on it, fixed boundary condition. And let's see here. I'm going to render it real quick so you see what I'm looking at there. And what I'll also do is I'm going to apply some loads. So the loading I'm going to do is just a sample load of maybe 200 axial kips downward applied on the top of that column. And then let's just do some lateral, maybe 10 kips in the X direction applied to that. So I'm looking at this model here. I'm going to just show you non-rendered, and I'm going to give it back. So we're just looking at a simple column, fixed boundary condition. And let's take a look at this model without P-Delta. So if we just solve that model without P-Delta, first thing we see is that big fat red warning. It tells us, per your request, that the AISC checks were done without P-Delta analysis. This means this code provision requires P-Delta analysis were ignored. So you can't really miss that big red sign. It tells us that, and that was the tools, preferences, checkbox that gives us this warning here, but allows us to get past it. So I can say OK, and I can come out. And now let's review this model a little bit. So in particular, I'm going to use a detail report, and then I'm going to look at this model. Oops, and for some reason I did not run this model yet. Let's see here. Let's double check. Maybe I forgot. I forgot to put my basic load case and my factor. Common mistake, rookie mistake there, but no problem. So we turn on the basic load case and a factor, and then we get to see it there. Okay, so what we can see here is using our model, we're going to look at our results better here. We get to see we applied the 200 kips, and we also applied moments. We calculated that 120 kips feet in the moment there, and a little bit of deflection. Now, the way we can always look at the deflection on the member, what I always like to do is look at the member, the joint deflection, so we can just indicate exactly what's happening on this model. So we have a little over an inch, 1.021 inches, that's going to be actually deflected at the top node. Now what we'll do is we're going to actually, let's mimic what P-Delta is doing. So P-Delta is applying secondary shears, and what happens is it deflects the shape. So we'll see here, if I go to my joint coordinates, after we've already deflected this once, I'm going to copy this roughly 1 inch, 1.021, and I'm going to put that at the X location. So if I dump that into the X location, internally this is what's happening. So the deflection is, we can see, is scooting it over just a little bit. And now by doing that, we can rerun the model just with that same loading there, solve it again, and we can see now that there's just going to be a little more moment created in that member. Things are changing just a little bit. Our deflection's changing just by the force of that leaning column there. Just by it leaning over, it's destabilizing it, and we're actually increasing moment, and we're increasing deflection. So what we'll want to do is keep going with this. This is where we're now iterating through the solution. So I'm going to copy that joint deflection. I'm going to go back into the joint coordinates spreadsheet and paste it right on top of that. So this is just for demonstration. This is what's happening internally in your model. You can rerun it, and you'll see here one more time that it's actually increasing there. So we're slowly increasing up from there. So 1.186, I'm going to copy that, and I'm going to put that in the in the joint coordinates, and I'm going to run the model one more time, solve current, and I can see here one more time, I'm going to look at the joint deflections, and it's still increasing, so we're going to keep going until we find that this number stops increasing, or at least comes upon a value we can say is now at steady state, or is that stops deflecting further. So I can see here, I'm going to use 1.19. It's getting to the point where we're probably within our tolerance, but you can just put that last number in here, 1.19, solve it one more time, and I'm seeing here the joint deflections is really staying at 1.19. So it is now resisting, every time I scoot it over, it's still resisting that, that deflected shape. So it's at the point where it's converged. So what we can do is we can just see that that happens the way the program tells us to do it, using the P-Delta. So instead of doing it manually, for demonstration purposes, I probably would never do that in real practice, but what I'll do is I'll bring back that joint coordinate over to 0, and we'll rerun this model, solve again, and we'll see here the joint deflections are a little bit higher there. I think we have to jump back to let me just double check one thing here. The joint deflections are probably, let's go back to our joint coordinates and make sure I have a 0 there. Okay, and we'll see, solve that one more time. We should get basically the exact same there. I'm a little high. I must be slightly off here, but we're getting the exact type of deflection there that we would see. So what we can see, let me just show you here quickly the little P-Delta effect as well. So if I look at my model, I'm going to go back unrendered. So I've accounted for P-Delta using the load combinations, but now what I have not accounted for yet is little P-Delta. The way you can account for little P-Delta is just by applying some joints to the member. So if I go ahead and apply these draw members, I can say split members, and I can split them into 5 different pieces and just add joints. When you're doing little P-Delta, it is important to say just add joints. That way you don't split into a ton of different members. The more members you get, it won't actually affect anything except you'll just get a lot more results, and you may not need to see so many results. So I'm going to just apply that there. And I got joints. The whole member is one continuous member, just joints have been added. And now if I run P-Delta one more time, I'll see that I get a little bit more deflected shape. Very small to change between that, but it's added a little bit more to my actual joint deflections. So let's take a look at this. Let me jump back here quickly to my slide of my example. And let's see here. So my example shows you here a little bit of what's happening. We see the differences here as they go across, what the change is there. If you see the numbers here, it's 1.021, goes up to 1.19, and we see that that change kind of levels out eventually here. The deflection of the little P-Delta here is going to come to a little bit more than that increase right there. So we've got a little change versus that. The next piece is to do is to take a look at our model and take a look at turning on what it means to do the adjust stiffness method. So what we had here is the 14th edition, and I have adjust stiffness turned off. The way adjust stiffness does, it adjusts actually the moment of inertia. So if you're adjusting the moment of inertia, that directly is going to be affecting the actual stiffness and the deflection. So if we say yes, iterative, which is going to mean that that it's going to actually iterate until it finds a solution that's close to what the tau is going to be, and it converges upon the solution for tau, which is the adjust stiffness factor. It's actually going to adjust that as it goes. So we're going to say yes, iterative, and now with that change made, any member that is considered lateral, and this member is considered lateral, let me just show you that there, the function is going to be lateral, then this will be affected. So if this is a gravity member, that iterative would not change anything. So let me solve this model, and I'll solve it with the adjust stiffness turned on. And we can see we jumped up to 2.342. So a lot more deflection happened when we added in that adjust stiffness. So adjust stiffness method is something that the code came up with in the 13th and 14th edition. And what you can see is that you also increased your moment by a lot by adjusting that stiffness. So the reason, really probably the moment would be what would more concern to you, although if you are designing towards a deflection, that would also be something that increased by a lot. And what you want to do is really think about where that came from. So the adjust stiffness method really kind of replaces the K factor that used to be in the older codes. The K factor was kind of just a fudge factor that was applied to adjust for these types of stability issues. And so now the K factor is always really going to be remaining at 1.0, which is our default. So we leave this blank, and the K factor is 1.0. And then if you're using the direct analysis method with the adjust stiffness on, that will take care of the factors that you were trying to account for in this K factor. So it should be a little bit cleaner, although you just need to understand what happens when this says iterative. It is really adjusting that internal moment of inertia as it goes. So that's definitely something I see a lot of folks get a little confused about. So that's a 96% increase. So it's a pretty large increase. So that would be something you would want to make sure you got. The other issue here is that we have a weak axis. We can try to look at what happens when we just flip around this column and take a look at it in its weak axis. So let me just go back into this column, and instead of being the strong axis of application, let's just rotate it by 90 degrees, and we can see here that that is going to be turned by 90 degrees. And then let's rerun our model. So we've got our P-Delta turned on, we have our adjust stiffness, and I try to run it, and it does not converge. It's a diverging model here. So what do we do to fix that? So first thing we'll do is I'll say, okay, I'm going to turn P-Delta off. And I'm just going to solve this model without P-Delta turned on. And let's take a quick look at our deflection shape. So without P-Delta turned on, that N2, which let's show our actual nodes here so we see what we're looking at. N2 is the top joint, and we see that the joint deflection for that N2 is 9.8 inches. So it's deflecting. Let's take a look at the deflected shape. Woof, it's flying off my screen. Of course, that's not really how it is. It's a little bit amplified, so don't get too upset here, but we have a 40% magnification factor on that. So let's just drop that to 5 so we can see a little bit more realistically what's happening. Okay, so we do have 9 inches of deflection though. So what happens internally, we'll do the same experiment we just did. We'll take that 9 inches and let's just see if we can, why it's diverging and what that really means internally. So in the joint coordinates spreadsheet under N2, let's just put down that 9 inches and see what happens if we try to rerun the model with that 9 inches as it leans over. So we can see that it is now going over about 23 inches. So we put the natural deflection of that first iteration, and we see it's 23 inches. I'm going to copy that. I'm going to paste that in here. And as I go ahead and run this model here, solve it one more time, I can see that it now deflects even farther, and that's 41 inches. So I'm going to go ahead and put that in here. Let's see. I'm going to keep going, and I can get here, 41 inches, run it one more time. And we see the joint deflections is now 65 inches. So it's super, it just keeps increasing. And what is happening is it's just not going to converge. It's just going to keep flying over. The more I push on it, the more it's actually just going to keep falling over. So really there's no resistance. It doesn't matter what happens. That column is not stiff enough in that direction. So in order to get that column to be stiff enough, we would have to, first of all, it's in its weak axis, maybe rotate it, or if we can't rotate it, maybe upsize it so it can resist that. But that's the classic case of why can't my model run, why am I getting a divergence? So kind of a specific, we see exactly what happens in that model. So let's jump back into our slides here so we can see, I plotted that out and we can see how this just sort of goes off and it will just keep kind of going off as we keep pushing on that. It's just going to keep on deflecting and it's not going anywhere. Whereas the other one, we had a chart that sort of leveled out for us. So that's your kind of a simple P-Delta an example. Another topic here is that we can choose to turn on P-Delta with a yes or a no, or we can also do compression only. This one's not as intuitive for me. When I first kind of looked at compression only, I didn't really grasp what that would make a difference. And what happens is you can see here for compression only, if we just look at a simple frame and we look at that as we apply some loads to horizontal loads, that we have some tension forces and we have some compression forces working in this frame. And that what happens is if you apply P-Delta, for example, to the tension member, so if we say we're turning on for just compression, then where we did it for the tension member there, what we would be doing is actually helping that tension member. That column there, if we push on it in this shear direction, we're actually resisting some of the load that you have applied, and it would reduce the tension in that member. So what you do is if you have compression only on, it would only apply it to members that are seeing compressive forces. So it's an additive to that versus trying to reduce it. So you're not really meant to take an advantage by using P-Delta. And so if there's a case, this is really not always the case, and usually yes is just good for most models. But if you see that P-Delta is helping your members, you might turn on compression only. This is the case where the P-Delta effect increases the flexural stiffness of a member in tension. So we don't really, that's not something that was meant to happen for P-Delta. So kind of something we can use if we have to, but it's not it's more of a case by case. So how do we get past P-Delta divergence? This is the most common thing that comes into support, and when you talk to folks, you say they're puzzled. How do I get past this? Because it feels like a big red screen and the stop sign really for you in your model. And so what we can do is, first of all, the first steps that we take over here in RISA to investigate a model would be to turn off P-Delta. So if it doesn't run, obviously there's not a lot of information we can take out of the model if it's not running at all, if it just halts your solution. So what we do is we just turn off P-Delta for any load combinations, maybe all of the load combinations, and go from there. We'll also obviously run the model. Once you have P-Delta off, you should be able to get past that. So now you can see what's happening in the model. And then the next steps will be to review deflection. So deflected shape will give you so much picture of what's happening in your model. That deflected shape is worth, a picture is worth a million words. It's great to understand exactly what's happening in the model, and it will give you a lot of clues. And then really design results is another piece of that. So these two work together. Sometimes you'll review both, and sometimes the one might not give you enough information and the other will. So these two items, the deflection and the design results, are really where you're going to be getting all most of your information. Possible problems, the most common P-Delta problems that we run into is going to be, as we go, instabilities is probably at the top of the list. I put it there on purpose because sometimes you just have an instability in your model. Maybe you turned on your P-Delta pretty fast in the design process, and you just have an inherent instability, and you're not detecting it, but P-Delta is detecting it because that'll be the first thing that hits is the instability. It'll go to the P-Delta warning versus the instability. So if you turn off P-Delta, you might see those instabilities, and that would be a good starting point, and keep going from there. So instability is something that we'll see here. Also, inadequately sized members. So the column I showed you where it wouldn't converge in its weak axis is a perfect example of inadequately sized member. It was not stiff enough to resist the P-delta forces. So we would have to size that member up or rotate it, as I mentioned, or just think of it maybe bracing of some sort, something to get past that sizing of that member. So we got to go beyond that. Tension and compression only members can cause you some P-delta problems. Usually they're not actually the problem, but you know, they're probably causing the problem, helping to cause the problem. So if you have tension and compression only members, what a lot of times we'll do is take them either to Euler buckling or to both ways and see if you still have a P-delta problem. If you still do, you're going to want to keep going from there and investigate it further. If you don't, then you can start to investigate why the tension and compression only members are causing that to go sideways on you. Stiffness adjustment, as we showed that one in there, it can cause you to now reduce your stiffness of your member as it gets adjusted, and then your P-delta will become a much more important thing. It will start to cause more failures and more divergences. So a good step in this path would be to turn off stiffness adjustment, as I showed you earlier, and then go to see if you can solve your P-delta from there. If you can get past it, then maybe we start to look at why the stiffness adjustment is causing it, and if that's a fair, if it really truly is a lateral member. Sometimes folks send their models into us, and they don't realize that lateral will be something that is the default, and so maybe they can switch a couple members to gravity and get past that. So you've got that, and then model errors. That's just a common one too, that maybe nodes are on top of nodes and things are not attached to each other properly, and things like model merge might help you there, but also we'll see how we can actually spot some of these things too as in some examples. So what I'd like to do is just start to review some examples, because I think this is the best way for you to learn how P-delta, how to get past it, is to see it, how I would do it in progress here. So what I'm going to do is let me jump into a model. Let's see here. So the model I want to start with is called large model. I'm not going to save that one. Keep going. So this model here is just sort of a frame, got some different things happening in it. Not a lot, just a different stepped frame. And it's got some loads on it. If we just look at some of the loading, some different area loads on this model. And what we'll do is just sort of, let's take a look. We've got some load combinations created, and what I'm going to do is just run the envelope solution. So let's solve the envelope solution. So as I solve this model, I can see that it's running behind the scenes here. It's solving each load combination, and the P-delta shears, if you can catch it, is happening as it goes. And what happens here is I get a P-delta diverging. So it tells me that there's an error message. It's giving me a P-delta divergence, and it's halting solution. Errors will stop your solution, so I don't get any results. And what I like to do is also look at what is the load combination that it stopped at. So I can see first the node. That might be helpful, but what also is that load combination. So load combination 8 is where it stopped its solution. So I'm going to come out of there, and I'm going to take a quick look at load combination 8. So load combination 8 does have P-delta turned on. So on my steps, I'm just going to go ahead and turn off P-delta. And I will do is I'll solve load combination 8. So as I look at load combination 8, I can see that there I've got, look at that model, and I can see it did run, which is nice. And let's take a look at first my design results. So this model has a variety of different shapes in it, and I can sort that. And let's see here. I'm going to sort the shapes, and I can see here that I have about 9. It looks like I have some members that are complete failing. It looks like 999. It's telling me as I scroll down here, and let's do it graphically too, so we can really see that. So if I look at unity shapes here, I've got a little area here that's really failing. So what's happening in this model is looks like some failing members. But let's see, let's beyond that, let's go back to wireframe for a second here. Let's take a look at our deflected shape. So this is going to tell me a lot more of the story. So it appears that that entire section where obviously those members are failing are actually going kind of off my screen. I really can't even see where it goes. It just goes beyond the screen. And this is a typical thing for P-Delta divergences where you can't really even see what's going on because it's just blowing off the screen. So what I can do is we can take a closer look. Now, I've worked with this model a little, and I looked at it obviously before I got on this webinar, so I know what's happening, but let's zoom in and see what's happening. So one of the things that has happening here is that we can see that this joint in particular looks like everything framing into that joint is pinned. So I have a pinned connection into a pinned connection into a pinned connection. So really this should be an instability. But what happens is along the whole model, there's enough to hold this all together that it does not become an unstable joint. So we can really get past this couple load combinations, and then really what happens is it becomes just an unstable joint and P-delta is applied to it. So what you can do to fix that is really just go ahead and give yourself some stability. Looks like probably maybe there was a column here, or maybe there was just some modeling, then what happened is maybe like we just forgot to make this fixed to fixed, so that's a continuous beam there. So what we can do is just double click that and give it some end fixity so that that is like more of a girder, and then it gets connected to its other side. So we see that this is now fixed to the other side of that, and everything else is framing into that now with pins. But there are now fixed to fixed, so that's continuous beam. And now we can solve the model one more time with load combination 8. And we can see now it's going to run. Let's take a quick look at our deflected shape. We can see our deflected shape, and it's still dipping. So it's probably not stiff enough, but it is not flying off our screen. So that would be the next step, probably would be to start stiffening it. But I could at this point maybe turn on P-Delta. Go ahead and say P-Delta is turned on, and we can run the load combination 8 and see if we can get past that. So now we see runs through P-Delta, and we still see that dip in there. We still probably want to address this weak area, but now at least we can see maybe that there was a need to put a column in that location. But this now tells us that we can get past that P-Delta. So it's kind of an example of an instability in a larger model and how we go from there. Let me also open up another model. It's called, let's see, it's a simple frame model here. Let's open up frame 1. And I'm going to say, don't save that. Let's go from there. So in this model, it's just a simple frame, and this is sort of a typical, hey, I have a frame, and it doesn't converge. I don't know why. It should be pretty simple, right? Why does this not work? So let's take a quick look. So I have some loads in here, and really I just have a little bit of some dead loads and wind loads and live loads. Not too much going on in this model. And when we solve the envelope solution, I can say right here, there's a P-Delta divergence. Okay, so why is there a P-Delta divergence? It tells us, we're going to go back to sleuthing this, so load combination 2, we see that. So what we're going to do is we're going to go back into load combination 2, turn off our P-Delta, and run that one more time. Okay, so it tells us we didn't do P-Delta, no problem. Ding. We get dinged for the instability. It's telling us there's an instability in that joint N2. Okay, so why is there an instability? So this is a classic model that folks have, the two-dimensional model, and they're trying to do it in a three-dimensional system, or three-dimensional modeling system, RISA 3D. So what you do to fix this is that we can take a look at our joint reactions, and we get this locked in here. Now the locked right there tells us that in the Z direction, the model is being locked, okay? So it's actually as if it's trying to fall in and out of the page. We didn't apply any loads in and out of the page. This is a two-dimensional model, and RISA knows that to some degree. So that's why it tells you, hey, I'll lock that for you, and I'm going to get past it. I'm going to give you results, but what I'm going to do is just tell you I locked it. So what you want to do to fix that, you don't really ever want to live with these locked. That's kind of a bad modeling thing. So even if you know, hey, I already know it's fine, just go ahead and fix the lock, and then you'll get past it, and you'll know for sure. So the way to work around that is I'm going to go to the boundary conditions spreadsheet, and I'm going to add some boundary conditions. So I'm going to tell the program to actually use all. So all of the joint labels are going to get a reaction in the Z direction. So you can just type in all, and you'll get a reaction in the Z direction, and then we'll solve it one more time. Okay, we're going to solve that load combination 2, and we'll see we got past that joint instability. The last step before you do that, since we put in a fake boundary condition, let's just make sure that there is no actual loads that are coming or reactions in the Z direction. And we can confirm that in the joint reaction spreadsheet. We see all zeros. So that makes us feel like, okay, I didn't do something that was incorrect. I can see that is correct. Okay, so now we are past that instability. So now let's try to run P-Delta one more time. I'm going to say yes, and I'm going to say solve the envelope and see if we can get past it. Okay, still a problem, still on load combination 2. I can't get past it. Okay, so what we'll do is we'll turn off P-Delta one more time, and let's solve load combination 2 one more time. Okay, load combination 2, what is load combination 2? It is just some dead load and live load. It's really not a lot. There's actually no wind load in this case. And what we can do is, let's say, look at our deflection. So the deflection sort of tells the story for us here. It tells us that, wow, this whole thing is sort of buckling, and just under its dead and live loads. So we can really see that there's probably not enough stability in this model to work with that. Now, this is the storyteller. Let's look at our design results. These still actually works, okay? So it tells us even with this kind of deflected shape, it's still passing, barely on 9.64 is barely passing, but it is passing. So what we might do here is we might turn off P-Delta for all load combinations and go ahead and say, we're going to say fill the block with and empty out all those so we don't have P-Delta on at all. And let's run an envelope solution. So now we can actually see that, yeah, probably as we go down these load combinations, we're going to start failing pretty badly. 200% is going to be pretty badly. So what we can do is start to size up these members. So this is a case where these columns are just not adequately designed. They are W10 by 39s, and they just can't withstand the loads that I've applied to them. So what I'll do is I'll use my suggested designs. So if I come in here into suggested design, really what I'm concerned with is going to be the columns. So these two columns is what I'm going to actually use for suggested shapes. And what suggested shapes does is it lets the program design the shape better than what I've used initially. So I have a 10 by 39. It's suggesting a W12 by 65 and a 14 by 74. Okay, so what it's going to do is I'm going to rerun this model. It's going to rerun the entire stiffness matrix using these new shapes. It asks me, do you want to do this for walls, beams, or members? I'll say all of them. We only have members. So as we go there, this is an iterative process because we just now increased the size of the members. We are still applying, we're going to be applying loads. It's going to be sizing it as it goes. So it looks like still we're not quite adequate for the member, this column M1. So let's go ahead and size that one again. I'm going to iterate one more time, solve again using suggested shapes. And as it goes, I can see here, I'm now closer, very close in that column. So let's call it a day here because what we haven't done yet is even turn P-Delta on. So let's just stop at this point. We have some upsized members, and what we'll do now is turn our P-Delta back on. So that's what we're really doing here, so we're trying to get past this P-Delta. So we'll solve again, solve that envelope, and make sure we can get past it. What it does is it gets past that P-Delta error, so we are now having no more P-Delta problems, but we are still not passing code check. So we might want to size this up a little bit more. So you can go through with that and let it size it as it keeps going. This isn't a symmetric model, so you'll notice I did it a little bit unsymmetric, so you'll have one weak and one strong axis, so it is suggesting different columns for each side. So this one in particular here just shows us how we can upsize the members to help get past that P-Delta problem. So next thing here we can do is let's take a look at a model I have here called house. So let's say no and keep going. So this model gives us a good, just sort of a simple frame, gives us an idea of what's going on in this model. It's got some cold form, some wide flange, different shapes in here. Nothing too different, but just in a standard house type frame. And what we can do is solve this model. Now the load combinations in here. Let's see. I'm going to delete this so we have no. So if we look at in here, we look at our load combinations. Just a lot of different types of wind loads on this model. And if I push the solve envelope, I'm going to solve the envelope here, I can see it's going to run through the different load combinations. It's doing the P-delta shears, and slowly here it starts to grind to a halt. You may be familiar with this. It's going to just keep going until it converges. So there's going to be a certain level that this will go. This might be where if you think you're getting really close, you could up that convergence, but probably I'm nowhere near that. So as it keeps going, it's trying. There's something that's causing this to go sideways on us. So we could wait until this fails, but I'm just going to cancel out of that. As I can see, load combination 6 is the issue. I'm going to kind of jump back in here and take a look at load combination 6. This is going to be a dead load case with wind load. And what we can do is we can turn P-delta off. So I can turn P-delta off, and I can say, let's solve this one more time without P-delta. So what all this has is just dead load with wind load in the Y direction there, or yeah, actually in the Y direction we're applying that. And let's say no, do not want to break the solution. So what we've got, if we look at the design results, we can see here we've got some failing members, a little bit. We've got different numbers here, a little bit overstressed, not entirely overstressed, but a little bit. And if we color code this, that's a nice way also to double check it. Just look at those unities and see. So some of this is overstressed. They're not really high numbers though, so not sure exactly why yet. But if I look at my deflected shape, I can see I've sort of got a crazy shape. And what's happening is that it's just not stiff enough to resist the loads that are being shown. So this is sort of one of those times where you can look at your joint deflections and start to see how high your joint deflections are. I've got upwards of 6 inches in the X direction. So I've got a large 10 inches there in that X direction. I've got large deflections in this model. And the reason I like to show this in particular is that this model, if we were just working off design results, would not give us the full picture. And a lot of times, you just think, hey, it's working, so I don't know why. But look, you can see these are smaller members. But really, you have to be looking at your deflected shape in order to get a full picture of what might be going wrong. What is really at this point is we need to size up these members or add bracing or some things in here. It looks like we do have some roof bracing in here, but again, these are tension-only cables that are very small. And so this could be causing us some of those problems as well. So maybe there's something we can do to help brace that instead of going about that and sizing up members. So a good demonstration of how deflected shape will be something completely different maybe than the design results, and you need to check both. So the last model I want to go into is a little bit bigger model, and it's called tower model. And I'm going to say nope and jump into this model. This model here is a more complex model, but it's going to be the same ideas that we look at. So if we look at this model here, just kind of a framework built next to each other, a tower type model. And if I go ahead and I look at here, I'm going to just show you, delete some of these so we can just look at this one load combination. So dead load, we've got some wind loads in here, and let's just try to solve this one load combination that I have. So what we see is that we have some P-delta divergence problems. So what I want to do, we only have one load combination to look at, so what I'll do is I'll turn P-delta off, and I'll just run this single combination. As I run this combination and I take a look at the model, so it looks like there's some tau stuff that's being adjusted there. So that's going to be, this kind of gives us a good note for the tau adjustment factor. So you might start to go into the 14th or 13th and say maybe no, and see if we can get past that. Let's take a look at our design results. So I don't see a whole lot of, let's see, I'm going to scroll down here. I don't see a whole lot of failures in here. I've got maybe 200% overstress there. That's enough that could cause us some problems. Let's color code it so we can see where that's happening. So if we look at that color coding, there's a couple little failures up there, and that could be causing us some of the problems. Let's show the deflected shape. So I can see here there's some deflection problems. It looks like my model sort of, the framework there is falling off there. So this is kind of where we start to look at what's happening, but it's hard to tell because it looks like the entire frame there is falling as it goes. So what we can do is we can sort of start to see what might be the whole mechanism that's sort of, where is the part that we have some failures at. So what I might do instead of looking at each single one of those members, because there's a lot of members and maybe there's just a point at which, and they're all deflecting actually together, which is a clue that these are all actually okay, it's just something that is failing as it goes. So let's go back to this a little bit. One of the ways we can detect what's happening in this model is we can do something in the load combination, and this is what we call like a load. We start to reduce the loads and slowly see when we can get to P-delta to converge. So let's go ahead and create a load combination. Let's call this P-delta 1. And in here we're going to turn P-delta on. Oops. And what I'm going to do is instead of, this is called nesting. So if you, I'd like to use the entire load combination 1. And so what I can do is I can use a nested load combination. I just tell it L1, and that will call up this entire column, row, which includes all of the items on that load combination. So L1 is that the 1 indicates that it's row 1. And then I give it a factor of, what I want to do is reduce that factor. So let's start with 0.75 and see if we can get P-delta to run with that point there. So I can say solve the current combination. And I can see it does not converge just yet with about 3/4 of the loads that I've had applied there. So what I might do is do another load combination. Let's call it P-delta 2. And in this case, instead of maybe 0.75, let's try half of the load that I've applied in that first load combination, and let's solve that combination. And now I start to get past it. So I'm close. I can actually, I'm about half the loads there. Let's try just going up a little bit more so we're right at the edge. And let's see if we can get maybe P-delta 3. Let's try to give ourselves maybe 0.55. Let's see if we can go all the way a little bit more loads that we have there, and see if we can get a little bit. So as it goes, it's struggling a little bit, but we do get convergence. So if everybody understands, what I did is I just pulled the entire load combination 1, and I just started reducing the factor. So every single one of these is being reduced by 3/4, then half, then 0.55. Okay, so and that one looks like just a nice amount so we can see exactly what's going wrong. So now I can actually show it did get past the P-delta, so I can start to see exactly, let's see what's going on with just a little bit of that P-delta turned on. And as I can see there, it looks like, if I zoom in, it looks like that one area is just flying off. If we zoom in, we can see that there's just one element that sort of is turning as it goes there. And so what that is, I think that looks like it's right there. So it's this element that's a vertical element there. And it starts to show me exactly what's happening in this model. What that is, let's zoom in a little. Let's look at our isometric view and look at that without it being deflected. So what that looks like there is if we double click on that, that's a rigid link. And so a rigid link shouldn't be deflecting like that, but what happens probably here is this is below it is a wide flange. It's just a 14 by 26. And what's happening probably here is that this is going to be trying to apply that is rigidly connected to my wide flange, and it's torquing that wide flange. So that wide flange can't resist that. And so what's happening is it's going to start to just twist out of the way. And so you might go ahead and maybe change this to an HSS shape that has a bigger J value or a torsional constant, because this one's pretty low, so it can't resist that torsion. But if you actually had something stiffer there, then you might be able to see that work a little bit better to resist that so that frame doesn't start to fly off the screen. So this method here just kind of walks you through taking each load combination and bringing it down slowly until you can get it to converge. So you say how that first one didn't converge with 75% of the load, but as we get a little bit, we try to get as much of the whole load on there as possible. So you might want to step through a couple different phases in order to see that, and that will help you investigate this model. So that gives us kind of a wide variety of different issues that we've gone through. We talked about the instabilities. We talked about models that just weren't sized properly. We've got models here and just some different methods to get there and how to work through it. So at this point, it's close to 1 hour. I think I hit about a 1 hour mark, and so we'll be around here for a couple more questions, but I would like to thank you for your attention and for watching our webinar today. It was a great topic with P-Delta. Thank you.